Okay, let's start off by taking a look at the week at a glance so that we're all kind of on the same page. Let me turn this stupid pen on. So today is Today my computer is totally lagging. There we go. Today's Monday. We're going to do chapter 13 plus, probably if we finish a little bit early, we'll do some review. I've got one video I want you guys to see. It's kind of interesting, and maybe it'll help you have an idea of what we mean by wave-particle duality, at least a little bit. Tuesday we have a test over chapters 10 and 11. Wednesday we're going to lecture on chapter 13, well, probably 14 by then. And on Thursday we'll start lab 12. It's on solutions. And then Friday we have no class.
Woohoo! Thanks, Jay. You're the best.
Well, I can't be here anyway, so. It's not because I love you guys at all. It's because I just can't be here.
I don't believe that.
Let's see. We will say that since we have a test, some of chapter 13 homework should be done Tuesday and everything, but we'll just say Thursday, all chapter 13 homework due. That way, you guys can focus on studying for the test tonight. You can work on the homework a couple other days. Or if you have the homework done already, is that what does Owen have it done already? Okay, just checking. So, let's see. We want to start in chapter 13, and you'll notice if you kind of read through chapter 13, we actually did the chapter somewhat in reverse order in that we talked about intermolecular forces and things before we're talking about some of the properties that we're going to talk about today, because those properties are all linked with or related to the intermolecular forces that we've been talking about. And so I thought it maybe was better to do it in the reverse order. So let's talk about pressure. Now, we're not talking about pure pressure. We're talking about things like atmospheric pressure and vapor pressure. And pressure is basically equal to the pressure equals force divided by area. So I guess technically that's a P. So P equals F over A. Now, we don't have to use the equation. We just kind of want to understand it, get us started on it. And what we can kind of think about it as is the number of particles striking the surface. Striking this an object. Now, pressure is one of those weird things where a lot of times we don't think about it on a day-to-day basis because it's constantly occurring to us. And so, you know, we don't say, oh, well, what particles are hitting us? But when we say that particles hitting us, what do we really mean? What particles are hitting us? This is sometimes a part of chemistry I think that's hard because it's a part of chemistry that's a little bit invisible. What's around us all the time here? Yeah, air. Number of particles striking the surface of an object. So what we're really talking about is the air. And so if you think about it, we have, miles of air pushing down on us. Or the other way to think about this is you can think about it kind of like a balloon. Here's Jay's lovely balloon. Let's tie it off down here. And, you've got random little particles in it. And what's keeping that balloon inflated is those particles striking the surface of that balloon. And so we can't see the air, and even though we breathe it, we need it to survive, it's constantly around us. We don't tend to think about it that much because of that. So we can look at atmospheric pressure. You want me to go back a second?
No, I was just making sure that's not how you spell it.
Is there only one L and two O's?
Yeah, I think so. Well, it's not that big of a deal. 2 L's. I was just like...
No, it's important. Jay should try to learn these things too. Let's see, did he spell it right in his... No, see, it's only got one O in my notes, so here. balloon. Now future generations will not be confused by my spelling mistakes.
I thought it was funny.
So we've got the atmospheric pressure, and this is basically the pressure exerted by all the gases in the atmosphere. Guess we'll worry about spelling gases in the atmosphere. And we can use a variety of devices to measure them. Probably the oldest known device, and I can never remember if it's a barometer or a manometer, I think it's actually a manometer, is simply a shallow dish filled with mercury. So that's liquid mercury. And then if we insert or invert a test tube in it, what we have is atmospheric pressure pushes down on that mercury. So there's my atmospheric pressure. And that causes the mercury to rise. Rises in the tube. And the distance that it rises above the surface, that's a measure of our atmospheric pressure. So the height of the mercury column is proportional to pressure. And so, for instance, what do we normally measure pressure in here in the United States?
PSI?
We can measure it in PSI. So if we take a look at units, I guess, units of pressure. There's 14.7 PSI, which stands for pounds per square inch. And if you think about it, that is a unit of force, pounds over area, square inches. What else do we measure atmospheric pressure in? Like if you're listening to the radio station, or the weather station, I should say. Yeah, millimeters of mercury. Oops, I guess we'll actually, come on, don't crash on me now. 760 millimeters of mercury. So the weight of the atmosphere pushing down in that pool of mercury will push mercury 760 millimeters high just from the pressure of the atmosphere pushing on it. Now, why do we use mercury in barometers instead of, say, water? Well, mercury's pretty darn dense, right? It's a very heavy element. If we used water, it would create a column over 30 feet tall. It's like 31 point something feet tall. So if we had to measure the atmospheric pressure pushing down on an evacuated tube like that, we'd have to, add like 2 more stories to this building to even be able to measure it. So one of the reasons we use mercury for things like that is because it is a very dense liquid. Sometimes you'll hear it referred to as torr, and that's named after some guy, some Italian guy that actually invented the whole thing, and so his name was Torricelli or something like that. You'll also hear it in terms of atmospheres, where they simply defined 760 millimeters as being 1 atmosphere. The technical unit is the SI unit, which is 101,325 pascals. And then there's one last oddball unit, 1,013 millibar. I don't even know where that one comes from. I just have it in my notes now. Of those units, if we were going to do the chapter on gases, we'd be using 1 atmosphere or 760 millimeters of mercury. Now, we're not going to worry too much about the set of units because we're not going to do any calculations of pressures. But I want you to have a kind of feel for them. So, kind of remember that number 760 and kind of think about it as, that's the pressure of 1 atmosphere. So, yes, so all of these are equivalent, meaning all these numbers could be used as a conversion factor if we were doing problems like that, which we aren't. Although maybe we should, just for fun. Maybe I'll make up a new worksheet just for fun.
Yeah.
Maybe not. I figure if you guys haven't figured out unit conversions by chapter 13, then there's just no hope for you anyway, so we won't bother. Okay, so atmospheric pressure. So we're still kind of continuing talking about that. Depends on temperature, but it's minor. And that kind of is what we refer to as low and high pressure systems in weather. It literally is, meaning we have more atmosphere above us than normal, or we have less atmosphere above us than normal, or it's denser. And then it also depends on elevation. So for instance, at sea level, atmospheric pressure really is 760 millimeters of mercury. But here in Rangeley, at about 5,280 feet, it's only 630 millimeters of mercury. And then if we keep going up, we find that, for instance, if we're on top of a 14er, so at about 14,000 feet, it's only about, oh, do I not have, oh, there it is, 462 millimeters of mercury. And then if you go as high as Mount Everest, which is about 29,000 feet. I love how we always talk about meters and centimeters and nanometers in this class, and then for whatever reason I measure all the mountains in feet. And that is about 277 millimeters of mercury. So one of the biggest challenges of climbing Mount Everest is simply the lower atmospheric pressure and thus the lower concentration of oxygen in it. And in fact, it's technically not possible to survive on the top of Mount Everest for more than, I don't know, like an hour, maybe half hour, something like that. It's very dangerous once you get up to the top, and you have to haul your own oxygen supply in to make it really up to the top. But apparently you get cell phone coverage there. They put a cell tower up there, or someone put a little station up there. I don't know, I think it's kind of funny. Hi, Mom, Dad, just calling from the top of Mount Everest. What? Yeah, I know, well, Mount Everest is cool, Rangeley is just kind of not.
Apparently that was priority.
I agree.
Makes sense. If there's an emergency.
Okay, so one of the reasons, so we've kind of hopefully got a feel for atmospheric pressure. Now what we want to talk about is vapor pressure. So this is kind of, you know, the sections of chapters where we're starting to talk about properties of solutions, and we'll talk about more properties of solutions in the next chapter. But the one that got kind of stuck here first was vapor pressure, and I think the reason we talk about vapor pressure first is technically if we hadn't skipped chapter 12, we'd know all about gases and things like that, and so that makes kind of a nice transition from talking about the properties of gases to talking about the properties of liquids. So what vapor pressure is the pressure exerted on the liquid. And what is pressure again? Yeah, it's the number of particles hitting the surface area. So the pressure exerted on a liquid by a vapor at equilibrium. Oops. Now I'm having trouble spelling vapor at equilibrium. And if we kind of think about it, we already know about this equilibrium a little bit. If I have a liquid in equilibrium with a gas, we talked about that already. What do we call those two processes? Bless you. So these arrows here are indicating equilibrium. And remember when we had the graph that looked like this, which part of that graph are we on? Solid, liquid, gas, and so we're kind of talking about being on that line, right? That's the equilibrium between liquid and gas, where we're converting from a liquid to a gas. I don't know if you guys remember those phase diagrams from last week. I don't know. Jay, did you watch the videos yet? Yep, evaporation is the process of going from a liquid to a gas. And what is the process of going from a gas back to a liquid? Condensation. So if we draw a lovely little beaker, or I guess technically this is a round bottom flask. Actually here, let's draw an Erlenmeyer. Maybe Jay's drawing skills have progressed. That is not a symmetrical one. That looks more like a foot. Whatever. It's an Erlenmeyer flask. Here, just in case you don't know or can't tell, we'll just label it Erlenmeyer flask. And of course, we're going to put a cork in it. And so here I've got my liquid. Oops, let's make a nice wavy liquid. And what we have to understand about vapor pressure is that we constantly have particles in the liquid going into the gas phase. And so this is going to be my gas up here. And we constantly have particles in the gas phase returning to the liquid phase. And so what we're talking about is that equilibrium means that the rate at which the liquid is evaporating is the same as the rate at which the gas is being condensed back into the liquid. So our definition of equilibrium, and we should point out that we're going to have an entire chapter on equilibrium. That's chapter 16. Now, we probably won't cover all of chapter 16, but we'll at least get there. And what it says is the rate at which molecules leave the liquid, or are evaporated really, is the same as the rate at which they return. Or that's our condensation. So we already know it takes energy to go from a liquid to a gas, right? Meaning if you have a pot of water, certainly some of it can evaporate, but a good chunk of it is going to stay in the liquid phase. And that it takes energy to go from one to the other, meaning we have to stick it on the stove and we have to boil it. But at any given temperature, some of the molecules are going to have enough energy to escape. So if we kind of make a plot like this, no. It's kind of like most of your rhetorical questions. I answer no, yet somehow you tell me or I do it anyway. I'm just practicing for if I ever get married. No. And then do it anyway, because that's yeah, it's probably better to not even say the no part. You're just saying give in gracefully.
It's probably better that you say yes and you don't do it.
Oh, yes, I meant to do that.
That's what we're expecting.
I should buy a little buckyball model kit and make Makita put together my buckyball.
What's that?
It's a form of carbon in which all the atoms are eventually connected back to each other, so it forms a ball. I'd have to Google it. I'll show you after class. We good to go, Jess? That little informational message brought to you by Jess. So if we take a look at the average kinetic energy of the particle, and we take a look at, actually, am I plotting the right plot? Make sure I got the axes right, because knowing my luck, I'd get it backwards. And actually, this is in your book anyway, so maybe I will have it backwards if I'm not careful. And let's see. Oh, this is, oh, I'm sorry, this is the number of particles. Yeah, see, Jay has to think for a second. Number of particles. This is the kinetic energy. And so if we take a look, we usually have a curve that looks like this, and it has a long tail going out here. So this is the average energy, and that would be proportional to what we would consider temperature. So we might say that this is 50 degrees Celsius. And if we take a second temperature, what happens is, at a higher temperature, that peak shifts out, and we're going like that. And so this might be 100 degrees Celsius. And remember, that's the average kinetic energy, and it's the number of particles at it. And so if this spot on our graph right here represents the energy required by water, for instance, to go from a liquid to a gas, go from liquid to gas, then notice that even at 50 degrees Celsius, some of the particles have that much energy. Oops, I meant to switch colors. So this is the number of particles at 50 degrees Celsius that can evaporate. And then notice that the red part, there's a whole lot more of those. You know, obviously at 100 degrees Celsius, lots of particles can evaporate. That is pointing to 100 degrees Celsius basically on our scale. And so what it's basically saying is that even at temperatures below 100 degrees Celsius, some of the atoms in a liquid will evaporate because some of the particles, remember the temperature of a liquid is simply the average kinetic energy. Some of the particles have more kinetic energy, some of the particles have less kinetic energy. For instance, when we put water at 100 degrees Celsius, does immediately every single molecule of water evaporate instantaneously or boil instantaneously? No, only some of them boil, and only the ones that have exactly that amount of kinetic energy or above. And so it's a process, and as we add more and more heat, we get more and more of those particles. So realize that temperature is that average kinetic energy, but that at any given temperature we have some particles that have more kinetic energy than that and some less. So essentially anything that you leave sitting out will eventually evaporate. I mean, if you leave a glass of water out in Rangeley, it's gone in like a day. It's so dry around here. Okay, so that energy that is that we're talking about, that you know, when we reference temperatures, is being compared to, or we've kind of already compared it to, the intermolecular forces, right? What did we say about the, you know, when the energy is high and the intermolecular forces are weak? Yeah, from Friday. I know that was like Friday, but you've slept, you've had a weekend. So if we have high energy and low intermolecular forces, then most likely something's going to be a gas, right? And that when the intermolecular forces, the amount of energy are about, you know, due to temperature are about equal, that's when we're in a liquid state. So same thing here. What vapor pressure is really doing, so we're coming back to our sort of vapor pressure topic, is it really is essentially a proportional to, or is measures the tendency of particles to escape the liquid. Measures the tendency particles to escape the liquid. And so if we have a high vapor pressure, and I should point out that V with a little subscript P stands for vapor pressure, just it's as good as anything else, means that something evaporates easily. Evaporates easily, which means that it has weak intermolecular forces. Meaning if it's very easy or it takes very little amount of energy to go from the liquid to the gas phase, that means that there's not very strong intermolecular forces holding those particles together. And then of course the exact opposite, a low vapor pressure, means that things evaporate slowly, which means they have strong intermolecular forces. So what we can really say is that vapor pressure is inversely proportional to the intermolecular forces. So this stands for proportional to, remember. And since it's 1 over something, that means inversely proportional. Means as one gets bigger, proportional, the other one gets smaller, or vice versa. If one is small, the other one gets large. Intermolecular forces, or International Monetary Fund, take your pick. Makes more sense if it's intermolecular forces, however. What? Where are we at, Jess? It says vapor pressure is proportional to 1 over the intermolecular forces. That's the number 1. Just checking. What comes after 1, class? Yeah, Brittany, maybe you better not come to the test tomorrow. Okay, so let's take a look at some properties of vapor pressure. Oh, it's not the most exciting topic in the world, but it's good to have the old Cody back. So it's independent of the volume. And so what that means is that if you have 1 drop of water, or you have an entire ocean of water, the vapor pressure that it exerts is exactly the same, which is good, because if vapor pressure was proportional to the amount of substance you had, then one way or the other we'd be screwed, because we go from having little drops of water in places to giant oceans of water. And so if I have a round bottom flask like this, and it's got a little cork in it, whether it's got a lot of water or a little water, doesn't matter. Now these are supposed to be the same size and everything. A little water, the vapor pressure is the same. Oops, I guess lots of water, little water. But the vapor pressure is the same, meaning the number of particles that we'd expect to be in the gas phase. I'll let you guys draw for a second before I guess I can put the second one. So it's dependent on temperature. And the reason for that, remember, is that temperature is about or proportional to the average kinetic energy of those particles. And so if I have a crappy beaker at 100 degrees Celsius, that's going to have, well, let's say not 100 because that's boiling, let's say 98 degrees Celsius. That's going to have a much higher vapor pressure than one at, say, 10 degrees Celsius. So here, I'm going to have maybe 1 or 2 particles in here. Here I'm going to have lots and lots and lots and lots and lots and lots and lots of little particles in the gas phase. We'll take a look at that in a second when we put up another graphic. You can kind of think about this as kind of like a hot shower versus a cold shower. If you take a hot shower, then you steam up your mirrors, right? If you take a cold shower, do your mirrors get steamy? Nope.
What is that? Is that AVG?
Average kinetic energy, AVG kinetic energy. So you learn that if you're going to talk fast, you also have to be able to write fast, meaning you start using more and more and more and more and more abbreviations in life. Or one can argue that you're simply lazy, like me, and so try to abbreviate as much as humanly possible because you get tired of writing. I don't know about you guys, but I have like a callus on my finger that's permanent from holding a pencil or a pen. I think most people do, because we end up writing a lot. Okay, so it's independent of the volume of liquid present, meaning it doesn't matter if we have a drop of water or an ocean. And then the third one is it's dependent on the, or depends on the identity of the liquid. Or what we're really saying is that it depends on the intermolecular forces present, meaning the vapor pressure of water is not the same as, say, the vapor pressure of ethanol. And we'll use that in an example here in a minute. For instance, yeah, actually we'll do our picture. This picture is in your book. I don't have my new copy of the book, so I don't know exactly which page it's on. In my old book, and you'll be able to recognize the picture anyway when I sketch it. In the old book, it was figure 13.4, and it was on page 306, which that's the 8th edition of the book. You guys got the 10th, so who knows what page it's on. And if I take a look, and I'm going to plot vapor pressure in millimeters of mercury, and I'm going to plot temperature in degrees Celsius of 3 different substances. And then the one point that we want to know on our graph is, of course, 760 millimeters of mercury, because that's atmospheric pressure. So we'll draw a dotted line across. And then we got 3 liquids, so we're going to need 3 colors. We've got, and this is about 35 degrees Celsius. I guess we'll move the 35 over. Sometimes I remember to photocopy this off and give it to you guys. This year I was lazy, apparently. So this is ethyl ether. Looks like this. Since you guys know what Lewis structures are. And then we're going to have ethanol. Do that in green. And then we want 76 degrees Celsius. And ethanol looks like this. And then last but not least is our buddy water. This graph is not to scale. So here's 100 degrees Celsius. And this is, of course, I guess we'll do it to be consistent, water. And I've got H-O-H. Now I know I just drew a whole ton of stuff, so I'm just going to take a break here and stretch out, maybe work out a few kinks from playing racquetball this weekend. It's good to start playing, although my arm hurts now. It's not a good sign. When? Oh, at the rec center. There are 2 racquetball courts there. So Jay Bradley Jr., how did you do this weekend at basketball?
As a team or for me?
As a team first, and then personally.
We went 1 and 2. We started off slow.
And personally?
I did all right. We did decent.
Who'd you guys beat?
CCU, JB.
CCU is who?
Colorado Christian.
Okay.
That's the number. We lost to Williston State. 8. And we lost to Gillette by more than that.
Okay. We have some home games anytime before Thanksgiving?
They just play at home this week 3 times. I'm not sure.
Holy cow. All right, lots of basketball to go watch. Does Sarah have some tests? Does Sarah have tests this week too? And Todd?
Oh,
Okay, so let's take a look at that graph and see kind of what we're looking at. So if I'm taking a look at the vapor pressure of those various compounds, which one has the highest vapor pressure at any given temperature? So notice vapor pressure's on this side. And if I just pick a temperature, say right here, who has the highest vapor pressure? Yeah, so at any temperature, it goes ethyl ether. It's going to have a higher vapor pressure than ethanol. Is going to have a higher vapor pressure than H2O. And so we would say that ethyl ether has a high vapor pressure. And of course, water then correspondingly has a low vapor pressure. At least, looking at these compounds. And so what can we say about the intermolecular forces in those? And I'm actually going to go and I'll sketch this on another sheet quick. Are you guys good to go on flipping or not? Still waiting. So Nikita, what do you got built over there? Now, does that violate the octet rule or anything strange like that?
No, not at all.
Not at all. We'll have.
Did a good job.
Oksana, you're not doing a good job as a mom here. You apparently have not taught the poor kid the octet rule yet.
Don't worry about it.
But it looks pretty good to me. You guys okay? I'll sketch the pictures again. So here we've got our ethyl ether. Here we had our ethanol. And here we had our H2O. So what can we say about the intermolecular forces between these particles? What type of intermolecular forces are present for ethyl ether versus, say, ethanol versus, say, water? Because we're always going to come back to the chemistry, and the chemistry means talking about the forces that are between these molecules. Oh, thank you. So remember, we said this had a high vapor pressure. This had a low vapor pressure. So this must mean that this has weak intermolecular forces. This has strong intermolecular forces. So what we're saying is, what do we mean by that? What intermolecular forces are present in that ethyl ether? Well, they all have LDF, right? So we can put LDF down for everyone. Yeah, London dispersion forces. And then if you look at the ethyl ether, it can have a very weak dipole. And we're talking about as weak as you can get, because that oxygen is partially negative, and each of those carbon ends would be partially positive. But it's very weak the way it's drawn. What about ethanol? What do we know about this part right here? Yeah, that's a hydrogen bond, right? So it's got one hydrogen bond. What about water? Yeah, two hydrogen bonds. So that makes sense. We know dipoles are very weak. We know hydrogen bonds are very strong. And so if we know the intermolecular forces between particles, we can make estimates, or we can actually perform calculations as to what their vapor pressures would be and what their boiling points and stuff like that are. And so an understanding of intermolecular forces lets us understand how things interact together.
Why is that one?
Well, there's only one OH group, right? And if you don't know what an H bond is, that's one of those topics that we did like Wednesday and Friday. So I don't know how many people are caught up on watching the lectures and stuff like that, especially with all the travel. Did you have good internet, Jay?
It just depended on the day. But I was able to watch some of them. I just wasn't able to watch Fridays part of the day.
Okay. Well, you really have to make sure you're up through, I think Wednesday was the last day we talked about Chapter 11. Maybe even Monday mostly, and then a little bit on I think we finish it up on Wednesday. And so, yeah, and then, you know, over Thanksgiving you can get caught up on the chapter 13 stuff since that's not on the test. So what the boiling point is the temperature at which the vapor pressure of a liquid is equal to the atmospheric pressure. So what we're basically saying is the vapor pressure equals the atmospheric pressure. And if we think about it, this kind of makes sense. Because if we kind of take a look at a liquid, remember we have atmospheric pressure pushing down on it. Notice that in this example I'm leaving the cork off so that we have atmospheric pressure pushing down on our solution. And so to form a bubble, and that's a really large bubble, right? That bubble has to be capable of pushing back the atmospheric pressure pushing down, or in order to escape, its vapor pressure has to be equal to the atmospheric pressure. So notice from the graph that I showed you, we can go back and we can say that if we took a look at ethyl ether, its boiling point was 35 degrees Celsius. Ethanol was 78 degrees Celsius, or 76, I don't remember, whatever I put on the graph. And H2O has a boiling point of 100 degrees Celsius. So if you look back in your notes, what I want you to note is where these lines cross 760, I drew a dotted line down and wrote the temperature. So in the vapor pressure, that's the red line, matches the atmospheric pressure. That's what we mean by boiling point. And heck, maybe I'll even sketch it again because, you know, I got some time to kill, I think. So if we take a look at our miniature graph here, this was vapor pressure, 760. This was temperature. And so what we're saying is that, oops. So here's the vapor pressure. And we'll just do ethyl alcohol, or the ethyl ether. And so that would be our 35 degrees Celsius where it crosses that. So this is essentially the boiling point. So if we take a look at the properties of boiling point and compare them to the properties of vapor pressure, we'll find that they're essentially the same, but not totally. So properties of boiling points. I should point out that we're almost getting a little bit more into physical properties than we are chemical properties. I mean, certainly those physical properties are tied to chemistry, but in this chapter and the next one, we're really talking about how, you know, particles dissolve, how solutions are made, and some of the physical properties more so than chemistry. So notice that it's independent of volume. Meaning the boiling point of a cup of coffee is the same as the boiling point of a swimming pool of coffee. Now what's different, and so I'll put this in red, this is kind of an aside, maybe a reminder, what's different is Q. So Q of a cup of coffee is not equal to Q of the swimming pool, right? Meaning which one has a lot more energy in it? The swimming pool, right? I mean, would you rather have a cup of coffee spilled on you or an entire swimming pool of coffee filled on you? Or neither, probably, would be preferable. It is dependent on the temperature, well, I guess on the identity meaning it's dependent on intermolecular forces. And in this case, notice that boiling point is inversely proportional to vapor pressure, but it's directly proportional to the intermolecular forces. So notice vapor pressure is on the bottom. If we have low vapor pressure, we have a high boiling point. And if I had low vapor pressure, that meant I had strong intermolecular forces. So that means that boiling point and intermolecular forces are directly proportional to each other. The higher the boiling point, the stronger the intermolecular forces in it. So think about it like sodium chloride's table salt. It's solid at room temperature, right? And if we compare that to water, which is a liquid at room temperature, we should expect that the ionic attractions between the sodium chloride crystals is much, much stronger than the hydrogen bonding holding the water together. So when we talk about those intermolecular forces, realize that the state at which something is in at room temperature tells us a whole lot about those intermolecular forces, right? Natural gas, CH4, only has LDF forces, right? It's a gas at room temperature. We get to water that has hydrogen bonding, it's a liquid. We get to sodium chloride that's ionic, that's still a solid at room temperature. So the intermolecular forces tell us a lot about what we can expect about something. Q is from chapter 4, that was heat or energy. Technically, the two terms are slightly different, but we don't worry about it in this class. And then the last one is it's dependent on elevation. So boiling point is inversely proportional to elevation. Inversely, well, it's dependent. Sorry, I guess if I'm phrasing it the way I wrote them before, I'll say it's dependent on elevation. If we kind of go back to the beginning when we were talking about sea level, we said the atmospheric pressure is 760 millimeters of mercury, and the boiling point for water is 100 degrees Celsius. But if we do rangely, then we said it's about 620 or something, and we find the boiling point of water is about 95 degrees Celsius. Or if we climb a 14,000 foot peak, which, you know, there's a few of them around here, then we drop down to 462 millimeters of mercury and 86 degrees Celsius. And if we climbed Mount Everest, which is 29,000 or so, then we said that we had 277 millimeters of mercury. Well, water only boils there at 69 degrees Celsius. So a lot of times for baking and cooking, we have high elevation recipes or high elevation versions. Although as far as I can tell, there's not much of a difference between rangely and sea level for most baking things. I mean, they say you're supposed to add like an extra tablespoon of water usually, or an extra tablespoon or two of flour. I've never noticed it to make that much of a difference. And this is also kind of the idea behind pressure cookers. Sure. Oh. Sure, yeah, this is something that's useful to know. So pressure cookers, one of the reasons we use them is at high pressure, we increase the boiling point. And so you increase the amount of energy that something's being cooked with. If you cook something at, 2 or 3 atmospheres, then water probably doesn't even boil until, 150 degrees Celsius. So you've got a lot more heat transfer to whatever you're cooking or doing with your pressure cooker. I don't know. Honestly, the only thing I ever remember Mom using a pressure cooker for was the can. And that's so long ago that I don't have good memories from that.
What?
Canning?
Oh, canning. I think it's a cannon.
Well, yeah, Mom had a cannon too, but that's a whole other story. Okay, I think that's where we're going to end here. Real quick, what I'm going to do is I'm going to show you a video, and I thought it was entertaining, so this This is just a little segment about the idea of wave-particle duality. And the way they're illustrating the wave-particle duality is they're using silicon. So silicon is a very nonpolar substance, meaning it has nonpolar bonds, and water, of course, has got hydrogen bonds and is very hydrophilic, meaning it loves to be with water. Silicon is hydrophobic. So the idea is that the water droplet does not want to be on the silicon at all. And so what happens is the water droplet will sit there and bounce on top of the silicon for a very long period of time. And the behavior as it oscillates back and forth, as it's bouncing, produces a wave pattern. And so this is not exactly quantum mechanics, but it gives us a visualization maybe of kind of what's occurring at that level, or it might allow us to see how things can behave as both a particle and a wave. So we'll go ahead and watch this.
We will never understand the fundamental level
That's a
of the
large
universe.
glare.
Our hopes of finding an ultimate theory will fail, and the human race will hit a roadblock it can't break through. But what if they're wrong? What if the truth about what happens deep inside you, me, and everything else in the universe is there? If we're willing to look for it.
I think.
For most of the 20th century, scientists believed quantum physics could not be explained. That we would just have to accept that we'll never know why things behave as they do down at the deepest levels of existence. But now, a growing band of rebel scientists thinks there may be a logical explanation for quantum weirdness after all. And new hope for revealing the ultimate truth of our universe. The trail begins here, with a drop of silicon. In his Paris laboratory, physicist Yves Coudet and his team conduct an amazing series of experiments. They are observing the behavior of silicon droplets bouncing in lockstep on a vibrating plate.
The liquid of the drop never touches the liquid of the substrate, so they're always separated by an air film. And in fact, this is stable. You can keep the drop bouncing on the liquid surface for several days if you wish.
Using a camera that shoots 1,000 frames per second, Coudet has discovered that these droplets mimic behavior seen in the quantum world. And that shouldn't be possible, because the quantum world and the large-scale world play by two different sets of rules. Yet here we see a single droplet moving randomly like a quantum particle, but behaving like a quantum wave. If you watch this carefully, you'll notice that the wave appears to be guiding the droplet. In fact, the wave fields around the droplets develop a memory of the trails they have followed. Despite their random behavior, they follow a small number of paths. Again, this is eerily similar to the behavior of quantum objects. This runs so contrary to popular belief that at first, Coudet refused to believe what he was seeing.
In any physics experiments, you only see what you are prepared to see. Of course, this was very obvious that there was a memory, but it took us some time to realize that it was that we were observing, because you have to adapt to this new idea.
Perhaps most revealing of all, Coudet has reproduced the double-slit experiment using his bouncing silicon droplets. The mystery of quantum mechanics is, how can things like electrons sometimes behave like particles and sometimes behave like waves? Perhaps this is the answer. They are particles and waves. Of course, this system, though small, is not quantum.
Our system is not a model of quantum mechanics, but it is an association of a particle and a wave, and some of its properties are similar to the properties that are observed in quantum mechanics.
Coudet won't claim that his experiments show us what is really happening down at the deepest layers of existence.
anyway, I thought it was kind of interesting, and you know, the idea that you can see how the particle and the wave interact with each other, and it's not exactly quantum mechanics like he says, but it does give us a big picture to kind of think about. And I don't know, maybe that's going to be my picture of the future for things like that. So I will post a link to the video too, and on the web if I get a chance this afternoon.
You said 7 o'clock?
I will be back up here at 7 o'clock.